This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to go over the common reaction types that you'll see on the test, and then we'll go over the concept of the mole and look at some common types of problems that you'll see. First, we're going to look at different types of chemical reactions, and you're going to see this notation where we have things like A and B and then AB combined. And what A and B equal is any element or molecule. So A could be equal to an element like potassium that we have down here, or if you look at the second example at the bottom, A could also be equal to an entire molecule like NO3 here. So then if that is A, then A shows up again on the other side of the reaction just like this. So just keep in mind A and B can be elements or molecules. I'm going to go over these pretty quickly because they're pretty straightforward, and on the test, questions like this are going to be pretty much just like recognition based. The first reaction is a synthesis reaction where you have two parts that combine to form a molecule that's made up of those two parts. The second one is a decomposition reaction where you have a molecule that's made up of two parts that then decomposes into those individual parts. Next is a single replacement where you have a molecule made up of two parts, A and B, and one of those gets replaced by C. So then we end up with AC, and the B is now kicked off, so plus B. Last one is a double replacement. So now we have a molecule made up of two parts that then exchanges one of its parts with another molecule that's made up of two parts. So one part of each of these molecules are going to exchange. So here we have the B exchanging with D, and then we end up with AD plus CB. And if we look at these two examples at the bottom, something you can do to make these easier is label the parts of the reaction on the left with the letters that we were using above. So for the first equation, we label the potassium A, the sodium B, and the chlorine C. And then on the right side, just see where those letters go. So sodium is B, and then KCl would be A and C. So then that one resembles the single replacement reaction. The next one, do the same thing. Copper is A, silver is B, and then notice how the NO3 shows up on both sides. So the NO3 as a whole is C, and then just track where those letters would be on the right side. So we have A, C, and B. So we also have a single replacement reaction for the second one as well. The next three reaction types are some more specific scenarios. The first one is a combustion reaction where you have a hydrocarbon reacting with O2, and the X and the Y in the hydrocarbon are just placeholders for whatever subscripts you would have for whatever particular hydrocarbon you're working with. And the hydrocarbon combines with O2, and then your products are going to be H2O and CO2. A really common reaction that a lot of people are probably familiar with would be butane, which is C4H10. And butane would just be the hydrocarbon that is in lighters. So just like a lighter that all of you have probably used before. And it combines with oxygen, and then what's being produced is H2O as water vapor, and then CO2 gas is being produced. The next one is a neutralization reaction where we have an acid, which is HA, combining with a base, which is the BOH. And for these two, the H of the acid combines with the OH of the base to form H2O. And then the A and the B are going to combine to form this BA, which is a salt. So sometimes you'll see it written as, they'll label that as a salt. And the reason that it's called a salt is because the A from the HA has a minus charge now, and the B from the OH has a plus charge now, and those two are held together with an ionic bond, and an ionic bond is the bond that holds salts together. So those would be technically a salt. This reaction will be covered way more when we go over acids and bases, but right now we're just going to leave it just at this. The last one is a redox reaction, and a redox reaction is what we call a reaction where there's a transfer of electrons. And what you want to look for to identify a redox reaction is a change in oxidation states, which we'll go over way more extensively in a redox reaction video. But this one you can see it really straightforward because the B has a positive charge, and then after the reaction the B has no charge, where the A goes from neutral to positive. So we've had a transfer of electrons from the A to the B, and that's what gets rid of the B's positive charge and then gives the A positive charge. A mole is a measure of quantity, and a mole is 6.022 times 10 to the 23 of that thing. And almost always on the MCAT, what it's going to be referring to is either atoms or molecules. So if you have 1 mole of an atom or 1 mole of a molecule, you have 6.022 times 10 to the 23 of that atom or molecule. For the MCAT, you can completely forget about the 0.022 and just memorize that number as 6 times 10 to the 23 because of the rounding that you can do on the test. And this number is also called Avogadro's number. Now let's look at the examples on the bottom of the screen. If you have 1 mole of carbon, like what we just said, that would mean you have 6 times 10 to the 23 atoms of carbon. So our next example, we have 4 moles of sulfur, which that would be 4 times 6 times 10 to the 23, and that comes out to be 24 times 10 to the 23 atoms of sulfur. The next 2 examples is the exact same thing, but we're applying it to entire molecules. So 1 mole of a molecule of NH4 means that we have 6 times 10 to the 23 molecules of NH4. And then if we have 3 moles of H2O, that means that we have 18 times 10 to the 23 molecules of H2O. Again, all we're doing is multiplying the number of moles by Avogadro's number. This next point is really important and it's really convenient, and it tells us that 1 mole of an element, the weight of that is equal to the magnitude of the atomic weight of that element, but in grams. So normally the atomic weight is telling us what the average atomic mass is, and that is in the unit of atomic mass units, which is referring to the weight of individual nuclei, so extremely small weights. And you can go back to one of the earlier videos in the course if you want to learn more about the atomic weight. But the magnitude of the atomic weight also gives us the mass of a mole of that element just in grams. So not atomic mass units, but grams. So looking at carbon, if we have 1 mole of carbon, the weight of 1 mole of carbon, you'd look at the periodic table, you would see the atomic weight is 12.011. So the weight in grams would be 12.011 grams of carbon. And what we're doing is multiplying the amount of moles by the atomic weight. So for the next example, sulfur, if we have 4 moles of sulfur, we're doing 4 times the atomic weight of sulfur, which is about 32. And I'm going to start rounding here to practice how we would do this on the test. And 4 times 32 equals 128 grams. So in 4 moles of sulfur, you'd have about 128 grams. The same idea can be applied to molecules. In the previous video, we talked about how to find the molecular mass, and 1 mole of a molecule is equal to the magnitude of the molecular mass, but this time it's in grams again. So for our example of the NH4, the molecular mass of NH4 we find by adding up the atomic weights of the elements within the molecule, and those atomic weights are about 14 and 1. So we do 14 plus 1 plus 1 plus 1 plus 1 for the 4 hydrogens, which gives us a molecular mass of about 18. So if we have 1 mole of NH4, then 18 is also going to be equal to the weight of 1 mole in grams. So 1 mole of NH4 is 18 grams. So when you have more than 1 mole, like what we have with water, 3 moles of water, you take the molecular weight and then multiply that by the number of moles. So water's molecular weight we find by adding up the atomic weights again. So you get 18 again, but this time we have 3 moles. So we do 3 times 18, which gives you 54 grams of H2O. So 3 moles of H2O weighs 54 grams. You want to make sure that you can work forwards and backwards with this. So the next example, we're starting with grams and we want to figure out how many moles we have. And you do this by dividing the amount of grams by the amount of grams that are in 1 mole. So if we have 56 grams of carbon, we divide that by the molar mass of carbon, which is about 12. And 56 divided by 12 is 4.66 moles of carbon in 56 grams of carbon. And then you could take that number of moles and then multiply it by Avogadro's number if you wanted to find the number of molecules of carbon. Which, if we want to do that here, you would get roughly 27 times 10 to the 23 atoms of carbon. Now we'll just apply the same concept to a molecule. So if we have 70 molecules of H2O, we're going to divide 70 by the molar mass of H2O, which is 18, and that equals 3.89 moles of H2O. So to find the number of moles, we would multiply that by 6 times 10 to the 23. With some rounding, we can basically round that up to 4 times 6. So that would be about 24 times 10 to the 23 molecules of H2O.